chlorine plus, what was it, potassium iodide? Yeah. Done? Let's take a look at another example. Let's take copper plus nitric acid. So why don't you go ahead and try to figure out copper plus nitric acid. Did I talk about the driving force last time? All right, do copper and nitric acid using single replacement pattern, A plus BX. One of the most common mistakes is people write Cu plus or Cu2 plus for copper, but that's copper ion, right? It's not copper metal. And what did you get for nitric acid?
HNO3.
Good. And what does it form?
H plus.
Well, this is going to fit the pattern, A plus BX pattern. And so we're just going to use the pattern. It's going to form AX plus B.
So, copper nitrate plus hydrogen?
Yeah, we're going to form copper nitrate, but which copper nitrate are we going to form? Copper,
Two.
yeah, right. That's good. Copper 2 nitrate.
You
So
want the higher number.
you want the higher charge, yeah. So we're just going to assume it goes all the way. So nitrate's minus, so we'll need 2 nitrates for every copper. So that'll be copper 2 nitrate. And then B is the element B. The element B is hydrogen. What's the formula for hydrogen? H? H plus or H2? H2, yeah. So to balance this, we'll need 2 nitric acids. And we're going to form hydrogen gas. All nitrate salts are soluble, so this is aqueous. This is group 1 or nitrate, and so that's aqueous. And so this would be it.
Oh, right.
Now, we want to know which way is the downhill direction. You know, if the forward is downhill, then this should happen. If the forward is uphill, then that's going to prevent this from happening.
What is that?
The driving force. So we want to know, is there a driving force for this reaction or no driving force?
There is.
Okay. For single replacement, we look at the activity series. So let's just take a look. When we look at the activity series, we compare the 2 elements, A and B. This is the activity series over here. And the way we read this is lithium is the most active, whereas gold is the least active. In terms of activity series, what this means is lithium, we know from the chart, is the strongest what? Reducer. And so the activity series is just looking at reducing strength. So lithium is the strongest reducer. It's the most active reducer, or the most active element. Gold is the weakest reducer. It doesn't want to lose its electrons. So reducers lose electrons. And so we compare the activity of copper versus hydrogen. Which one's more reactive? Copper, the element, or hydrogen? And so one way of thinking about this is this. If you were to fill the trunk of a car with copper versus filling the trunk of the car with hydrogen, what would be your preference?
Copper.
Copper? Copper or hydrogen's... No, not weight-wise. Let's say if you had a kilogram of copper versus a kilogram of hydrogen, then it doesn't matter weight. So It's the same weight. So if you had the same weight, what would you rather have, copper or hydrogen? Well, you know, with gas mileage, you probably want with the lightest, but here, copper or hydrogen, but if they're the same mass, then it doesn't matter. So we're going with liquid hydrogen. Copper or hydrogen? Hydrogen, still hydrogen? Still, in other words, which one do you think is less reactive, safer in the event of an accident?
Copper.
Copper would be probably safer because hydrogen might end up in a Hindenburg type scenario. Yeah. And so what we say here is that hydrogen is more active, that is more reactive, it's easier to lose electrons than copper. Copper is less active. If it's less active, it's more stable. And so what this is this is an uphill reaction. If it's uphill, then we think about water. Does water flow uphill or does water flow downhill?
Down.
Water flows downhill, so this reaction's not going to happen. This is trying to flow uphill. This is like trying to make water flow uphill. And if that's the case, what we do is we say that there should be NR. You know what NR stands for?
No reaction.
No reaction. So if I were to take copper and mix it with nitric acid, according to single replacement, we expect
No reaction.
no reaction. So let's take a look at a video, copper and nitric acid. So copper and nitric acid, we predict no reaction. So nitric acid is just this clear, colorless liquid, and then we have some copper wire twisted in. Do you see any evidence of reaction?
Yes,
It turned green.
color change.
Yeah, color change.
That's a plus two oxidation state.
Yeah, right. There's definitely, and then there's some kind of gas forming in here. Do you see that gas?
Yeah.
Now it's really starting to bubble. You see all the bubbles of gas forming? So, it's not wrong. What we did with single replacement is correct. And we expect there to be no single replacement reaction. So I need to fix this. There's going to be no single replacement reaction. No single replacement, because there's no driving force. This is an uphill single replacement. So no single replacement. But there's definitely a reaction between copper and nitric acid. Now it's getting hot. As it gets hotter, reactions speed up. And so you can see lots of gas forming here. And then this green solution is turning dark blue. And so the next thing I want you to try is try the CHARP method and see what you get.
Can you repeat again how this is an uphill reaction one more time?
It's uphill because what's stable and unreactive, so this is less reactive. If it's stable and unreactive, it's lower. So, if I have this is a microphone, it's kind of heavy, but if I put it up high here and it's not very stable, then that's what we call active or reactive. But if I lower it and then just place it down here, then it's a lot more stable in terms of. That's where the uphill comes. Right, and so this is what we say is this is higher in energy, this is lower in energy. So what we want to do is we want to go lower in energy.
So how do we determine how active they are?
We determine it by the reactivity of the elements. So for example, gold coins versus copper coins. Which one will be, in other words, which one will be more reactive, which one will be less reactive, you know? And both of them are coinage metals, but the gold is going to last longer than the copper. You know, the pennies, I speeded it up by heating it up, but do these pennies look very good anymore? No, but if I did the same thing to gold, it would still look pretty good. You know, I could heat up the gold and it's still gonna, in fact, I could heat it up so hot it melts the gold and it still looks fine, yeah. But,
So would we look at the oxidation, oxidizers and reducers for that?
well, we look at the chart.
Oh, the chart method?
Well, there are two charts, and they're both the same chart. We look at the activity series. And so you look at the pattern, like the group 1, in fact, the group 1 and the alkaline earths are very reactive. And so lithium, potassium, barium, strontium, calcium, sodium, those are extremely reactive. In fact, they're so reactive, these are reducing agents, they're so reactive, they'll react with a very weak oxidizer. Do you know what's a really weak oxidizer? There are lots of them, but water is one of them. And when we think about water, we don't think of it as much of an oxidizer, but all these metals will react with water, in fact, explosively. So if you mix potassium with water, you get an explosion. Sodium with water, an explosion. Magnesium, aluminum, manganese, zinc, chromium are a little bit less reactive. And so this requires steam or acid. And so we look at these metals, and they get less and less. Platinum and gold are extremely unreactive. So
the better
the more stable it is,
more activity.
the lower the energy, the more stable it is, the less active.
So it reacts with the weak oxide.
And so hydrogen versus copper, we just see which one's more reactive. Well, hydrogen's more reactive, copper's more stable.
So for single
This is uphill.
replacement, you would look mainly at the elements?
Yeah, the two elements. The two elements are in the activity series. The chart here, this is why that chart there is upside down. Did I talk about this chart on the wall?
Yeah.
The chart on the wall is upside down because they wanted to show the activity series. The activity series is based on reducing strength. So lithium is at the top of the activity series. This one loses electrons most easily. And then we go down. And so this is ranked in terms of activity series. Lithium at the top. Gold's not on here. Silver's on here. Gold will be down here somewhere. Platinum as well. Fluoride's at the bottom. And so that chart over here is really ranked based on oxidizing strength rather than reducing strength. And so the activity series is just a chart based on reducing. Now there's a conjugate relationship. The conjugate relationship is this. If something is a very, very powerful oxidizer like fluorine, it takes 2 electrons. Once it has those 2 electrons, it doesn't let go. If it doesn't let go of the electrons, then it's very hard to remove the electrons from fluoride. And so what this means is if fluorine is a powerful oxidizer, fluoride is a very weak reducer. In fact, fluorine is the most powerful oxidizer on the chart. Fluoride is the weakest reducer on the chart. It's conjugate. And so it's a seesaw relationship. If one side's powerful, the other side's got to be weak. Otherwise, it doesn't make sense. And if one side's weak, the other side must be powerful. So if we look at lithium ion is going to be the weakest oxidizer on the chart. If it's the weakest oxidizer, it really has no attraction for the electron or pull for the electron. That means when it does get the electron, it's loosely held. So lithium has very loosely held electrons. It loses them quite easily. because lithium ion doesn't really hold on to electrons very well. So if this is a weak oxidizer, which is the weakest oxidizer, then this is going to be the most powerful reducer. And so that's called the conjugate relationship here. And so it doesn't matter how the chart's written, or if we only look at one side or the other side. You know, the activity series is just defined that way historically, but we could have looked at the oxidizer instead. So we can really compare B plus to A plus here, compared those. But historically, it's just been easier just to compare the elements. And so this is why the activity series has come about in that way. But anyway, take a look at the chart method for this and see what you get from the chart method.